So hello everyone. We today have Shubhrajit Bhattacharya who will present on the introductions to Galois representation. He already gave many presentation in this Saturday series. And so over to you, Shubhrajit.
Thank you for the introduction.
Your voice is a bit feeble, so can you speak louder?
Yeah. Now you can hear me.
Now perfect.
Yeah. And the slides are also visible, right?
Yeah.
Yeah. So as the title says, it is a very brief introduction to Galois representations. First, I will just give a little introduction about the Galois group, which we will be studying. So, as we know that number theory is mostly the study of number fields, and that can be summarized as the study of this absolute Galois group, which is the Galois group of the algebraic closure of Q. And this can be defined as the inverse limit of all the Galois groups of the finite extensions of finite Galois extensions of Q. So here's the definition of this Galois Q bar over Q. And then by definition, these finite Galois groups are given the discrete topology because they are finite, and that's why they are compact groups. And by the definition, this absolute Galois group is a closed subgroup of this product. And we know by Tychonoff's theorem that product of compact spaces is again compact. And a closed subset of a compact set is again compact. And that's why the absolute Galois group is a compact group. And being a projective limit or so this inverse limit is also known as a projective limit. So being a projective limit of finite groups, this Galois group is a profinite group. And we'll be denoting by G sub Q. And the topology that it gets from this product topology is known as the Krull topology. And by Galois representations, we actually mean that representations of this group or maybe some special subgroups of GQ. Like we sometimes we consider Galois representations of the absolute Galois group of this local field QP, and this absolute Galois group occurs as a subgroup of this whole absolute Galois group of Q. And we also sometimes consider representations of while group or
So this
way
particular
group.
local Galois group is the decomposition subgroup, right?
Yeah. This is isomorphic to the decomposition subgroup
Of the main Galois group, global Galois.
Yeah. And the decomposition subgroup is defined to be the sigma, all sigma inside GP, such that no, not GP. Sorry.
GQ.
Yeah. GQ. The all elements sigma inside GQ such that if you fix one, say if you fix one extension W of the periodic absolute value P of Q on Q bar, then sigma dot W is equals to W. That means the set of all elements inside GQ which fixes this absolute value. So this is the decomposition group, and it is isomorphic to the local Galois group at P. So for finite extension, we can talk about that sigma of a prime ideal. Sorry?
Yeah. Sorry, I was asking, can you write this GP is the inverse limit of some sequence of groups?
I'm sorry, I couldn't hear you. Your voice is breaking.
Can you write GP as an inverse limit of a sequence of Galois groups?
ZP.
If you can't hear me,
ZP?
never mind. Please continue. Okay.
No. So he was asking if this local Galois group is
ZP or GP?
GP he's talking. This local Galois
yeah,
group
GP
is
is similarly defined. GP is similarly, you can define inverse limit of all finite extensions of this local Galois
field.
Yeah. So where K is running over all finite extensions of this QP.
Okay, thank you.
Okay. So now we just give the definition of a Galois representation. So we mainly consider uh, topological fields while considering a Galois representation, but we sometimes also give discrete topology to the vector space we are considering. So let F be a topological field and V a finite dimensional F vector space. Then the vector space F gets a natural topology from the topology of F, and GQ is equipped with the crude topology. Then a Galois representation is just a continuous homomorphism between these groups GQ and GL and F. Or this is also the same as GLV. Since the dimension of V as a vector space is in, this is isomorphic to GL and F. Sorry, yeah. So in many cases, we consider, like we said, that special subgroups like GP. So for those cases, there are certain terminologies that we use in standard literature. Like when F is a finite field of characteristic P, then we call it a mod P representation. Also, if F is say the algebraic closure of a finite field, and we denote it by Fp bar, then we also call it a mod P representation. Again, if GQ is replaced by the Galois group of a p-adic local field, here p-adic local field, by p-adic local field, I mean that it is a finite extension of QP. So, and if we consider a p-adic local field K, and if we consider the absolute Galois group of K, then all its representations in the field QP, we call them p-adic representations, and it is a separate field of study which is known as p-adic Hodge theory. So I guess I have mentioned it in my previous presentation, right? Yeah. So
Yes, you did.
but when K is a p-adic local field and we are considering the vector space over L-adic field, say QL, where L is a prime different from P, then we have a very special theorem of Gratentic, which is known as the Gratentic Monodrome Theorem, which I will be mentioning in the final slide. So, which will make it clear that why we didn't need an L-adic Hodge theory. Because so in this case, when L is not equal to P, the case is much simpler than when L is equal to P. And when we replace GQ by the Way group, which will be defined later, and then we consider some special types of representations with a special condition. They are called Way-Deligne representations. So before that, we first saw that why we don't
So
consider
because of three,
complex. Sorry.
because of three, we do not need much knowledge about the L-adic vector space and related arithmetic. Only p-adic.
Yeah, we need that. We need that, but to understand the structure of p-adic representations, like p-adic QP valued vector space for a p-adic local field, we need some very sophisticated ring theoretic constructions and so on. So they are known as p-adic Hodge theory. So all started with a construction of Fontaine, which is known as the Deram ring of p-adic periods, which is denoted as BDR, which I will come to in later slides. But there is a monodromy theorem which says that we don't need to define such rings, etc. The case is much simpler, and that's why we didn't need a specific theory for that. So is it okay?
Yeah, continue.
Okay. Yeah. So now we show that why we don't consider complex valued representations. So while talking about representations, we might think that the field C is the most natural thing that should come in mind, but we are only concerned with periodic fields, etc. So we see that for complex representations of a number field, say k a number field, and uh, we have the absolute Galois group of k, and if we have a com if we consider a continuous complex valued representation, by complex valued I mean representation in GLNC. So then we will show that this representation actually factors through a finite extension of k, and that's why we don't bother about complex value representations. So I have included a detailed proof of that. I will not maybe go through the complete proof. So it uses this fact that for any n greater than equal to 1, the group, this matrix group has an open neighborhood of In, which contains no non-trivial subgroup of GLNC. So this is proved here. So by open neighborhood, I mean in terms of the natural topology that comes from C. So I have included a complete proof, and using that, I am claiming that if I have a representation of this absolute Galois group in GLNC, and it is continuous, then rho factors through a finite Galois group, that is Galois L over K. So that is equivalent to saying that there is a map rho bar, which is in this diagram. So we have a map rho bar from this finite Galois group to GLNC, and this absolute Galois groups surjects onto this Galois group, and this diagram is commutative. So this map is simple because you take any element sigma inside K bar. You take any and restrict that to the field L, then it will be an element of Galois L over K, and this diagram will commute. So that's what I mean by factoring through a finite extension. Yeah. So is the statement clear?
Yeah.
Yeah. So once it factors through a finite extension, then this representation will be easier to study. So there is no interest about such complex representation.
How do you use the previous theorem there?
Yeah. I use the previous. I use lemma 1 to prove lemma 2. Yeah. So here is the complete proof. One can go
could you just say that these absolute Galois groups over any of these fields, they are totally, in their topology, they are totally disconnected.
Yeah.
Yeah, and
so profinite groups are totally disconnected.
And GNNC is a connected group.
Yeah.
And so the continuous maps, from this, the image must be finite.
Yeah.
I don't know exactly all you're saying now, but I think that seems to be the main idea.
Yeah. Maybe that is the main idea, but there is a well-known proof using this fact, and that's what I have presented here. Yeah. So it is exactly using the fact that GLNC is connected in some way, I think.
Yes, GLNC is connected, whereas these absolute Galois groups are totally disconnected.
Yeah, that is totally disconnected.
And therefore,
and that's why the image has to be finite. Yeah, and since the image has to be finite, and that's why it factors through a finite extension.
But where are you using this subgroup lemma, or is that what you are really saying?
Yeah. In the proof, I am taking a subgroup W to be an open neighborhood of W of I, such that it doesn't contain any non-trivial subgroup. So now let rho being continuous, then we have that this inverse image inside GK is open, and that is also open neighborhood of the identity element inside this GK. So therefore, it contains some open normal subgroup, Galois K bar over L, right? For a finite extension L over K. So because these are the basic open sets in the Krull topology of GK. But then its image, the Galois K bar over L, which will be a subgroup contained inside W. But by lemma, here it should be lemma 1. But by lemma 1, we know that there are no non-trivial subgroups of W. And that's why this subgroup has to be 1. And hence we have that GK quotiented by Galois K bar over L is equal to Galois L over K. And thus we get the result.
Basically, number theoretic objects,
Yeah.
finite extensions of the rationals.
Yeah.
Now, to introduce this topology, this is a different structure.
Yeah.
And so this is
Yeah,
a convenient structure, and that makes, for after getting expertise in this topology, you see how natural everything is.
Yeah.
However, to do any further work, you really have to go to the original setup, that these are finite extensions of the rationals or whatever. And those are the books that we are really studying.
Yeah.
And so working out one example there, or a few examples, is a lot of work.
Yeah.
This topology is a convenient language.
Yeah. Yeah, so this makes the complex representations quite not interesting for us. So we'll study p-adic representations. So this p-adic Galois representation of GQ is a topological vector space V, which is a finite dimension. Sorry.
I should tell you one of my memories.
Yeah.
This subject can be also talked about in non-standard analysis. You know that subject?
No.
Robinson. He started the non-standard analysis. And he gave a lecture in which I was present, and Andre Way was also present.
Oh, I see.
And so Andre Way was talking to him, and he said, what you are saying is a convenient language, another language.
I see.
It's a convenient language and makes some things better understandable for those who pick up that language. However, the original problems, they have to be solved separately. They have to be solved in going to the original setup.
But the philosophy can be understood in a different way in sometimes.
This is a convenient language. You see, to create a language to communicate to each other.
Yeah.
That is a big issue in any developing a theory.
Yeah.
To develop a correct language, but that understanding that language becomes a separate project.
Yeah.
And so most of the people like me who come from analysis, topology, geometry, they do not know this language.
Yeah.
And therefore, this fortunately, in my graduate studies, I tried to understand all these languages together. So I roughly know what you're saying. But let's go ahead.
Yeah. Okay. Sure. Yeah. So here, V is a finite dimension. Yeah. So here V is a finite dimensional QP vector space. So here QP is the so I talked about this in my earlier presentation, that QP is the field of p-adic numbers with the p-adic topology. And if we give the vector space the discrete topology, then it will again factor through finite extension, and that can be seen easily, because for a discrete topology, the image will be again finite if we consider a continuous representation. So we give V the p-adic topology, and then we see what happens. So if we give the, so if we consider any general representation of a p-adic field of p-adic representation of the absolute Galois group of Q, then the image, then that representation will be similar to another representation rho bar or rho prime that will have image inside GLN OK. That is the matrices. It will be the matrices. It will have as image inside GLN K will have entries in the ring of integers of the field K. Yeah, so this is a theorem in Diamond-Schurman's chapter 9. This is proposition 9.3.5. So is the statement clear?
No, whatever the statement, this group is GLN OK. GLN of ring of integers.
Yeah.
That is actually compact.
Yeah.
Yeah. That's the so from the infinite, from the non-compact object, you come to some compact object.
Yeah. That's the so that's the importance of this theorem. Yeah.
Yes.
Yeah. And another thing is, if you consider any algebraic extension K of QP, and you consider rho to be any continuous representation of GQ, which takes values inside, I forgot to write that, which takes values inside GL and K. So you can maybe consider the largest such that is, you can consider a representation in GL and QP bar. Then the image, but then the image rho will have entries inside the GLN of L, which is a finite extension of K. Yeah, sorry, which is which will be a finite extension of QP. Sorry. So even if you are considering a representation with coefficients in the algebraic closure of Q bar QP, if you assume continuity, then it will take values in a finite extension of QP. This is another important theorem, and this needs, I think, yeah. So the proof needs the Baire category theorem. Yeah, so one can prove that if you take any compact group, if you take any compact subgroup of this GL and QP bar, then that compact subgroup will be contained inside some GLN F, where F is a finite extension of QP.
And actually in the GLN of the ring of integers.
No. GLNF is just the field. F is just a finite extension of QP.
But
and yes, by the previous lemma, then it will have image in the ring of integers.
Now you are considering compact subgroups of GLN QP bar.
Yeah. Yes, that is a theorem that if you take a compact subgroup of GLN QP bar,
then it will be under the representation.
It will be contained inside GLN of F, where F is a finite extension of QP.
Not just GLN F, but GLN of the ring of integers in F.
Yeah. That will be true by the previous lemma.
Yeah, okay, but I mean that's a better statement.
Yeah. That's a better statement. Yeah. Those so this can be this should be replaced by OL. Okay. And yeah, so and this follows from this theorem, and this theorem is proved in this small paper of Keith Conrad. given in the reference. Yeah. Yeah. So compact subgroup sub GL and QP bar.
Where is this paper published? On archive or
No,
what?
no, it is no. It is just a 3-page, like it is an expository article type.
So
Yeah, just a note, because this theorem is well known, but it is not very well written in any book or etc. Yeah, so that's why he just wrote it and put it up on his web page.
Okay.
Yeah, it's just 3-page proof, just simple periodic analysis.
Yeah, so.
And since this Galois group is compact and we are considering a continuous representation, the image will be compact and hence it will be contained inside a finite extension. So that will be the proof. Yeah, so we just recall some notations here. So we know that decomposition group surjects onto the absolute Galois group of this finite field, which is also isomorphic to Z hat. Z hat is nothing but the inverse limit of all the cyclic groups. And the kernel of this natural surjection is denoted as IP, the inertia subgroup at P. And thus we have this canonical three-term exact sequence for each P. And we will denote by P, a Frobenius element at P, which will be a canonical topological generator of GFP. And by sigma P, we will denote any lift of that Frobenius element or the canonical generator of this topologically cyclic group Z hat inside this decomposition group.
Yes.
Yeah, so yeah. Now I present the very first examples of Galois representation. So the first example is that I can maybe the simplest periodic representation of GQ is the periodic cyclotomic character. And that can be defined as the Tate module of the multiplicative group GM. So the multiplicative group GM, if I put the K bar in the multiplicative group, then it will give us the all the non-zero elements, and the group of all non-zero elements of K bar. Sorry?
What is Tate module of multiplicative group?
Yeah, so I will just give the definition here. Yeah. Yeah, so for any elliptic curve, the Tate module is like this. So you take an elliptic curve over K. So the Tate module for elliptic curve will be the inverse limit of all the L to the n torsion points. Okay. Yeah. So you just consider this exact sequence and how I define the P to the n torsion elements. So P to the n torsion elements of the multiplicative group is nothing but the P to the nth roots of unity in the algebraic closure K bar. And that's why it is isomorphic to, if we assume that the characteristic of K is not equals to P, then it is just isomorphic to Z mod P to the NZ. The group of all P to the nth roots of unity inside K bar. And from mu P to the n plus 1 K bar to mu P to the n K bar, we have a natural map, x going to x to the P. And with respect to these maps, we can take the inverse limit, right? So this is how we define the Tate module of the multiplicative group. And by the definition of a inverse limit, the elements of this Tate module will be like compatible sequence, what we say. And by compatible, we mean that it should satisfy this equation, x to the n plus x sub n plus 1 to the p equals to xn. So we choose a particular element in this state module, which is tau, where epsilon naught is equal to n, epsilon 1 is not equal to 1, and epsilon n to, and in general epsilon n plus 1 to the p is equal to epsilon n. So then we see that one can prove that this state module is isomorphic to tau times ZP. So now how we define the p-adic cyclotomic character? We just define this chi p of sigma is equal to lambda n, and an element inside the state module, such that sigma of t is equals to lambda times tau, which is this compatible compatible sequence. Say all epsilon n to the power lambda n. This is a little complicated definition, I think. So yeah, so is this clear definition?
Somewhat, not totally.
Yeah, so you just take yeah, so the chi p of sigma is defined by like chi p of sigma is equal to this element, and what this element does, like if you apply sigma to t, then it will give you lambda times t, where this product is defined in this way.
What is GP star? It's GP star?
Yeah. ZP star means all the units inside ZP.
Okay.
Yeah. So one can check that its values are all units in ZP. So this is a very important example of Galois representation. One-dimensional, and we sometimes twist some Galois representations by this character. So we say that ZP1, this is a standard notation. ZP1 is defined to be this state module of the multiplicative group, that is the p-adic cyclotomic character, and we define QP1 to be the tensor product with QP. So if I tensor with QP, then it will become a QP one-dimensional QP vector space, right? So this is a ZP valued representation, but if I just tensor with QP, then it will become a one-dimensional QP representation. Yeah. And in fact, one can show that if you take any one-dimensional p-adic representation V, then we have V equals to QP times E for some, say E is a generator of V as a QP vector space. Then one can show that sigma of E is equal to chi p of sigma dot E for all sigma inside GK. So like this p-adic cyclotomic character determines all one-dimensional representations, one-dimensional p-adic representations of GK. And also if K is Q or QP, then chi p is surjective. So there are more details about this, that when these representations are unramified at which primes. So one can check that the p-adic cyclotomic character is unramified at all primes, all primes Q not equals to P. And also one can show that chi p of sigma q, sigma q is the Frobenius element, the lift of the Frobenius element at q, then chi p of sigma q is equals to q for all primes q not equals to p. So these things are in these references I have given. So in a similar way, one can define the Tate module of any abelian variety defined over K. So we just take the inverse limit of all the p to the n torsion points. And then if we just tensor it with QP, then it will become a QP vector space, and it will be denoted as VP of A. So in general, if the characteristic of k is not equal to p, then and if the dimension of the abelian variety is g, then this state module will be a 2G dimensional p-adic representation of G. Is it 2G or?
It is
No,
a
I guess
module over this GP.
Yeah. Tate module is over GP because AP to the n is a GP to the n module, right? The P to the n torsion points that can be thought of as a subgroup of GP to the n. GP to the n times G. Yeah, for an elliptic curve V over Q, you know that the M torsion points are exactly isomorphic to Z mod M square. Yeah. So in this way, so if you take the P to the n torsion points, then it will be isomorphic to Z mod P to the n Z whole square. So if you take the inverse limit, then it will be just ZP squared. The Tate module will be isomorphic to ZP square for elliptic curves over Q. And if you tensor it with QP, then it will become just QP squared. And now we have, so I just included the famous theorem of Said. So it states that if U over Q is an elliptic curve without complex multiplication.
Something you missed, I think, in last slide. That about isogeny thing.
Yeah. So I have just mentioned that with respect to which I am taking this inverse limit. So it is almost same as this thing. Here it is multiplicative, x going to x to the p, but here it is additive. The group structure in the points of abelian variety is additive. I have just assumed that. And here the isogeny is the multiplication by p map.
I see.
So if you take a point inside the p to the n torsion point and multiply it by p to p, then it will become a p to the n torsion point. Yeah, so that's a natural map, and with respect to this, we take the inverse limit and define the Tate module. And now we state the Serre's open image theorem, which says that if you have a elliptic curve E over Q, which is without complex multiplication, that is the endomorphism group of E is isomorphic to Z. Then the Tate module of E at some prime P, which is a p-adic representation as we have seen. So denote that by rho E sub P, then the image of this, then the image of GQ under this p-adic representation will be open and hence will be of finite index inside ZL to ZP. And moreover, this representation is surjective for all but finitely many primes P. Yeah, so some very recent results I have found and does put it in the reference, which talks about the index. How large can this index be?
How much is the difference between this image and the Tate module itself?
The image of this Galois representation actually is important in some studies, like Serre once proved a theorem about, once proved a very effective version of the Chebyshev density theorem. And he used the image of a Galois representation in his paper very much. And that's why it is sometimes very important to see how large the Galois image is. So this theorem says that the image is very large in some sense because it is a finite index. So there can be some representations which will have image of infinite index. So in some sense it will be small. But here Serre's theorem says that if you have an elliptic curve without complex multiplication, and then the Tate module the image of the Galois group under the representation attached to the Tate module will have a very large image.
Now, it's the finitely many primes. So it's easy to prove this general theorem, but to have any investigation of how finite, what finite, then
No. I haven't seen that.
Those are thesis after thesis after thesis, such things.
Yeah.
Yeah.
So for example, so
That is the real work that is needed.
Yeah. For example, Faulting's theorem says that there are for curves of genus G greater than 1, there are finitely many rational points, but
That's
we
a
don't know
serious
how
theorem.
finite.
That's a serious theorem.
Yeah.
That's a
Yeah.
serious actual.
But still we don't know how finite it is.
Yeah. Again, that issue is there. No, but that
Yeah.
Faulting's theorem is a serious theorem.
Yeah. That is definitely a yes. Yeah, but some
It's a real
recent
advance in
effective
knowledge.
results have been there.
Real
Yes,
advance
yeah.
in knowledge, not just language, not just developing a language.
Yeah.
I think assuming ABC, there's some effective result even for faulting, but that assumes ABC.
Sorry.
Now, I was just saying that assuming ABC, there were some results for effective bounds in the fault for faulting.
There are some results and people are keep.
No. There are some developments. Say Chabuti-Coleman method. I know that. You can search that Chabuti-Coleman integration or Chabuti-Coleman method. They've developed some method to describe the number of rational points in a variety of genus G greater than equal to 1. So yeah, so there are many recent works of Jennifer Balakrishnan on that theme. You can search her.
We will have a talk on this
research
on
papers.
22nd March.
Oh, I see. Yeah. That Chabuti-Coleman method is basically to understand that how finite or how much or how large can that finite set of rational points be. Yeah, so now I just briefly mention what are Weyl-Deligne representations. So the Weyl group at P is defined to be the inverse image of this cyclic group generated by the Frobenius element inside this GFP. So this is Z hat, and this is generated by this Frobenius element at P, topologic generated. That means if you take so this notation is just the cyclic group generated by Frob P. So if you take this cyclic group generated by Frob P, and if you take the closure of this, then it will be equal to Z hat. That's why it is called topologically cyclic group, because it has a dense cyclic subgroup. So if you take that cyclic subgroup, and if you take the image, if you take the pre-image of that under this map, then it will be denoted by the WP and known as the Weyl group at P. So here we have a map V, which takes every element G inside WP to a unique integer inside Z. So this is also isomorphic to Z, and that's why one can think about this map V as a integer valued map. So a Weyl-Deligne representation of WP is a pair row and specific operator n inside the n by n matrices of with elements in F. Where rho is a continuous representation from WP to GLNF, or where F is a field, and GLNF is given the discrete topology, and n is in particular matrix inside this M and F, the n by n matrices with elements in F. which is also called the monodrome operator. I don't know why this is called the monodrome operator, but I'm just stating the definition, which satisfies this identity. So rho g times n times rho g inverse is equals to p to the minus v of g. So this is this v. So v of g times n for all g inside WP. So if f is equal to ql, the L-adic numbers, then we say that rho is an L-adic Weydelian representation. And so one considers the category of all such Weydelian representations of WP. And there is a theorem which makes this Weydelian representation interesting to us, that if you take any continuous L-adic representation, here I should say that L is not equal to P, only in that case. So if you take any continuous L-adic representation of GQP, then and that is d-dimensional, then there exists a uniquely determined nilpotent matrix, d by d matrix inside this MDQL, such that if you take G equals to H times some sigma p to the n, where H is inside the inertia group, then we have this identity. So it's like that. If you take any continuous L-adic representation, it restricts to Weydelian representation. On the Way group. Yeah, so one proof can be found in the reference I've given here. Yeah, so is this clear?
Not very much, but you can proceed.
Yeah.
Yeah,
Yeah, so the proof can be found here. So there are some steps in the proof. Yeah.
Without that, how can it
Yeah.
be clear to us?
Yeah.
I understand what you're saying.
Yeah. So please correct me if I am telling anything wrong. Yeah, so here are two monodromy theorems, and I don't know the proofs, but I am just stating because almost every standard book on p-adic representations state these two monodromy theorems, which shows you the difference between L-adic and p-adic representations. So yeah, so instead of looking at the whole category of all L-adic representations of GQP, so this is the category of all continuous L-adic representations of this Galois group of QP. This is the Galois group of absolute Galois group of QP. So we sometimes look at the category of all L-adic potentially semi-stable representation. So what is a potentially semi-stable representation? So if you take an L-adic representation rho of QP, then it will be called potentially semi-stable if you can find an open subgroup H of the inertia group at P, such that if you restrict rho at H, then its characteristic polynomial will be just x minus 1 to the power dimension of rho. So it's like the simplicity condition on the representation. So a representation call is a representation rho is called semi-stable when you can take H to be the whole of IP itself.
Simply,
And
it seems like that, but what is stable thing here?
He's not defining stable, he's defining semi-stable. And
Yeah,
potentially
semi-stable.
So there is some kind
semi-stable
of
means yeah. So these notations are not really clear. I have asked some of the teachers, they have taught me these things. So they have said that these many of the notations are not clear really. Like this, why this is called monodromy theorem is not really clear.
Then this is potentially semi-stable. Instead of giving you the last definition. So I think it's a matter of working. carefully working out what the original references are and how did this theory arrive in the first place.
Yeah. Yeah, but I had asked about this thing, Professor Eknath Ghate. So he told that there cannot be very strict reasons for these notations or
I think it's just
or
a
these terminologies.
feeling.
Yeah. Whatever they felt and they named it. Yeah, so it is called semi-stable when you can take H to be equal to IP, but potentially semi-stable when you have to take possibly a proper open subgroup of IP.
Yeah.
I think
And
semi-stability of the
Gratentic's-
elliptic curve is defined in terms of their reductions, right?
Yeah.
Additive reduction and multiplicative. What is it?
Yeah, I'm not quite sure about the proper definition, but yeah, it is defined in terms of its there are three types of reductions, right?
Yeah, additive, multiplicative. One is other.
And there are, I guess.
Hassan, do you know? He's not here. I think.
Really, I don't know.
Oh.
Maybe this is.
What is semi-stable elliptic curve? Do you know?
Yeah. For example, sometimes in mathematics there are some words that you can find in many places without relationship. For example, the word splitting field in Galois theory has a meaning, and a splitting field for a division algebra, for a central simple algebra, has other meaning. And these two things has no relationship really. So maybe there is no relationship, but I don't know. Maybe exactly there is an exact relationship.
No,
I
but
don't
just I
know.
wanted to recall that semi-stable elliptic curve. What is that?
That's a competitive.
Semi-stable elliptic curves. Yeah, the elliptic curves that has multiplicative or good reductions.
Yeah.
Yeah. Yeah, so semi-stable is avoiding the additive reduction. Yeah.
Yes.
Yeah. And yeah, so when L is not equal to P, this is not true. So then we have to define the what is called the Theorem representations. And for this to define, Fontaine defined the ring BDR of periodic periods, which are analogs of periodic periods. So like this is an analog of the 2 pi I in the complex algebraic geometry. And this gives this complicated looking comparison theorem between two different cohomology groups. Like this is the Ital cohomology group and this is the Theorem cohomology group. So BDR was discovered in order to get this comparison theorem. So a similar comparison theorem is true for complex algebraic geometry, and the goal was to get a similar comparison for periodic case also. And that's why the BDR was discovered. And if you have a periodic representation, the V, then one defines DDR of V to be the tensor of V with BDR and taking the GP fixed points. The GP acts on this B tensor V on BDR, and then you just take all the
DRAM.
Sorry.
DDR.
Yeah, DR is DRAM.
No, capital DDR that you have written. Define DDR.
Yeah, capital DDR is defined in this way. V tensor with BDR, and then take the GP points. So here I think it should be. Yeah, so there is a mistake here. I think Yeah, no, no, yeah, so it's all right. Yeah, so yeah, so you just take all the elements here which are fixed by this GP. And we say that B is Theorem representation if you have the dimension of QP of DDR is equal to dimension of QP of P. So we know that it's always true that dimension of QP DDR is less than equal to dimension of QPP. But when it is equal, then the representation is called Theorem. And if we consider the category of all Theorem representations, then we have this p-adic monodrome theory. That p-adic representation of GP is Theorem if and only if it is potentially semi-stable. That is, there is a categorical equivalence between these two categories. So this is why we need p-adic Hodge theory because of this ring BDR. So shall I continue?
Okay.
Yeah. So now Galois representations attached to modular forms. So we know that Delin first attached a Galois representation to the very well-known modular form of Ramanujan. That was the delta function he defined. And after that, it was generalized for all modular forms, and not all modular forms, but certain Hecke eigen new forms. So Hecke eigenforms means that modular forms which are also eigenvalues, which are also the eigenvectors of all the Hecke operators. So so the theorem is that let F be a Hecke eigen new form of level n and weight k. Then we know that the field generated by all the Fourier coefficients of F is a finite extension of Q, and we say that this field to be Kf, and let L be any prime, and let be a prime of Kf lying above L. So then there exists a continuous representation which is dependent on F and the prime we choose above L, lambda, representation of GQ for inside this GL2 of Kf lambda, which is the completion of Kf at the prime lambda. And this representation is unramified at all primes dividing L times n, where n is the level of the new form. And the image of the Frobenius at any prime script P lying above P, which is not dividing L times n, satisfies this characteristic polynomial x square minus AP of f x plus p, where AP of f is the pth Fourier coefficient of f.
Did you define what is ramification of Galois representation?
Oh yeah, sorry, I just forgot to write that. The representation rho is said to be so rho is said to be unramified at P, unramified at P if rho restricted to the inertia group at P is trivial. That is you take a representation of GQP or maybe GQ, then IP is a natural subgroup of this thing, right?
Yeah.
Then if you restrict rho to IP, then if you get trivial representation, that means it just acts trivially.
Is there no role of that script prime?
Sorry?
Is there no role of that script prime P that lies above P in this definition?
No, the Frobenius elements are just all the Frobenius elements at the primes lying above P are all like conjugates of each other.
Okay.
So if you take a different prime above P, P1, then the Frobenius element of that will be just conjugate by one element of the Galois group, from of P to sigma. So that's why up to conjugacy, the Frobenius element at P is Frobenius element at P is unique. So it doesn't depend on the choice of the prime you are choosing lying above P.
Okay.
Yeah. So is this definition of unramifiedness clear?
Clear.
So when a representation is unramified.
Clear. Go ahead.
Unramified means trivial, right?
Yeah. Unramified means when you restrict to the inertial group.
Mhm.
Yeah.
So in the representation, some upper triangular matrices do not form a normal subgroup. That is what it means. Yeah, and then these are these.
And here is the modularity theorem, and it says that
Yeah, we have heard this. Yeah.
What is MF here?
What is?
sorry.
Capital MF. How you are relating that?
Yeah. So capital MF is the level that we have to consider for this. So
What is
that level was defined, I think, by Sayre.
No, how you are relating with the form F, I think, right?
Yeah. So M is dependent on the modular form. So yeah, so I'm just stating that. So the modular Galois representations are just irreducible Galois representations, two-dimensional, such that the determinant of rho is the same as the cyclotomic L-adic character, and there exists a modular form if for the congruent subgroup gamma naught of MF for certain integer MF, such that there exists a prime lambda of K F lambda lying above L, such that the representation attached to that modular form is similar to the representation rho. Now we can reduce the representation modulo L and get a model representation. So Sayre's conjecture was that all two-dimensional model representations which are irreducible and odd are they are modular, and this was finally proved by Khare and Wintenberger. We know that. And using all that, one can prove Fermat's last theorem, that if you have a solution, non-trivial solution to the Fermat curve, that is a to the L plus b to the L plus c to the L equals 0, then first Frey was first to consider this elliptic curve, and using all this theory we could prove that this elliptic curve is not modular.
In your second line, there is two-dimensional L-adic, and then later you are saying two-dimensional mod L representation.
Yeah. So I am considering the representation modulo L.
And in the initial,
if you take a
modular-
representation which is so if you take a representation which is taking values inside GL to QL, then we have seen in a previous lemma that actually its images are inside GL2 of ZL, right? The ring of integers. And then since the elements of the entries of matrices are elements inside ZL, we can reduce them modulo L, right?
Okay.
Yeah, so we can just reduce them modulo L and get a representation which takes values inside GL2 of FL bar. Yes, so that was all my presentation, and yeah, so I have listed the references and the links from which you can find the PDF.
Thanks. Anyone has any questions? If there is no question, let us thank Shubhrajit for wonderful talk.
Yeah, nice talk, very clear.
Thank you, Shubhra, for very nice talk.
Thank you.
Thank you.